Hello everyone, I'm Yavuz Selim Inan, and I'm excited to share with you my research project, Adaptive Multiscale Retinal Diagnosis, a hybrid trio model approach for comprehensive fundus multi-disease detection, leveraging transfer learning and science networks. Thank you for your attention. My study focused on addressing the global challenge of visual disorders, which afflict over 2.2 billion individuals worldwide. Timely and accurate diagnosis is critical to prevent impairment and blindness. Through the development of the hybrid true network model algorithm, my study seeks to achieve early and accurate detection of both common and rare eye diseases. My research utilized the retinal fundus multi-disease imaging dataset, RefMet, consisting of 3,200 de-identified fundus images for algorithm training, validation, and testing. In image processing procedures, I ensured optimal quality by implementing cropping and histogram balancing techniques with multiple filters. To enhance the effectiveness of the analysis, I balanced the data for each disease through oversampling methods. In my study, I employed the binary revealance method to establish a multi-disease classification system. This innovative system allows for the independent detection of multiple diseases in a single diagnostic process. Each disease detector incorporates finely-tuned hyperparameters and consists of three feature components: a classical transfer learning convolutional neural network, a two-stage CNN model, and a Siamese network. Subsequently, the features extracted through this trio network model approaches underwent principal component analysis, and predictions were made using voting classifiers and machine learning algorithms. Let me introduce the first component of my model, transfer learning via efficient NetB3. This cutting-edge approach involves fine-tuning a pre-trained CNN by adding two layers whose dimensions and properties are optimized during hyperparameter tuning. The CNN is initially trained on the vast ImageNet dataset, allowing it to leverage learned patterns and reducing the need for extensive data in medical imaging. In the second component of my model, I combine manual feature extraction methods with CNN via efficient NetB0. This unique hybrid approach broadens the range of detectable features, proving invaluable, especially in scenarios with limited data. To begin, I employed 8 detection using stable filters, emboss, and posterize effects. Following this, I further processed these features using the efficient NetB0 architecture, a deep convolutional neural network. Throughout this process, I utilized the binary cross-entropy loss function as my training loss function. The third component of the model leverages a Siamese network architecture, which plays a pivotal role in the few-shot learning approach, especially useful in scenarios with extremely limited data or for very rare diseases. Siamese networks focus on learning a similarity metric between input pairs, aiming to minimize the distance between similar items and maximize the distance between dissimilar ones. This approach is a part of meta-learning, where the network learns to learn from small datasets, making it highly effective for few-shot learning tasks. Subsequently, the features extracted using the trio network model approach undergo principal component analysis. Then, predictions are made using voting classifiers and a variety of machine learning algorithms. This feature processed with an ensemble of machine learning algorithms, including decision tree classifiers, random forest classifiers, logistic regression, support vector machines, and key nearest neighbors. This comprehensive strategy ensures robust performance even in scenarios where data distribution is skewed, making it a powerful solution to the issue of data imbalance. These graphics display a receiving operating characteristics curve based on the testing set. The analysis of various models reveals notable results: an impressive average accuracy of 97%, with the highest accuracy reported for ODE at 99% and the lowest for ODC at 92%. The balance between precision and recall is quantified by an average F1 score of 78%, with OD recording the highest at 90% and ODP the lowest at 55%. In discussing the results, I want to draw your attention to the table that compares the computed F1 scores with the benchmark F1 scores for different eye diseases. This comparison, along with the percentage difference, illustrates the effectiveness of my hybrid neural network model algorithm in diagnosing both common and rare diseases from retinal photographs. It's clear from these findings that my approach yields significant improvements over existing benchmarks. This underscores for potential of my algorithm to enhance the accuracy and the reliability of retinal eye diseases diagnosis, ultimately leading to better healthcare outcomes for patients. In conclusion, my research introduced a hybrid neural network model algorithm leveraging the binary relevance method using fundus images to diagnose 12 common and rare eye diseases accurately. This includes Dursens, optic cupping, tessellation, age-related muscle degeneration, retinitis, optic edema, optic pallor, diabetic retinopathy, media haze, branch retinal vein occlusion, and myopia. Thank you for listening me.